And now let's go to my presentation here about multiaxial fatigue, the role of multiaxial storage state in the hydrogen-assisted rolling content fatigue in bearings for wind turbines. Modern, the so-called clean energies, maybe they are not so clean. My co-authors are Miguel Lorenzo and Diego Vergara of the Fracture and Structural Integrity Research Group of this University of Salamanca, the oldest in Spain. We are approaching 800 years old in 2018. Now we are 797, like a typical number for planes, for jumbo planes, and we are very old, the oldest in Spain. And this is a beautiful logo with the castle, the lion, and the bishop. You can see this castle and the lion in the Florida State logo because Florida a long time ago was Spanish. Summary, introduction. The problem is that bearings of offshore wind turbines are prone to suffer hydrogen-assisted rolling content fatigue, HARCF, because of long-line lubricants, additives favor hydrogen generation, likelihood of moisture entering the bearing, very confusing and complicated problem. Salty environment with probability of hydrogen penetration, and there is no scientific reference related to bearing failure in harsh environment. But the companies, for instance SKF in the Netherlands, apparently this was performed, this research, in the framework of the multi-high European project. Multi-scale approach to hydrogen embrittlement of crystalline materials. One of the industrial partners was the SKF in the Netherlands, who manufactures this bearing for wind turbines. And they have problems because of premature failure of this bearing due to, supposedly, hydrogen-assisted cracking rolling contact fatigue. To simulate, the aims of the world are to simulate the so-called ball-on-rod, 3 balls in a rolling over a cylinder, over a ball, over a rod, ball-on-rod test, over a rod, rolling contact fatigue, hydrogen-assisted rolling contact fatigue. We have to simulate by the finite element method in order to obtain the multi-axial storage state inside the bearings during service. From it, first of all, stress state, mechanical analysis, and from it, the steady state concentration, distribution of hydrogen, chemical analysis. This is the mechanical part, this is the chemical part. Thereby showing where the material of the bearing could be damaged by hydrogen, the places where hydrogen diffuses for a long time. And thus to gain a better understanding of the influence of hydrogen on the service life of offshore wind turbine bearings through this numerical study. Let's go to the problem statement. This is a so-called ball-on-rod test. 3 balls rolling over the rod, on the rod. This is the rod, a cylinder, and these are 3 spheres, 3 balls with different, the dimensions are here. This is the 3-dimensional problem with the planes of symmetry. We assume material elastic, perfectly plastic, and this is a typical Young's model, Poisson coefficient, and yield strength, very, very high yield strength, high strength material for bearings. The numerical modeling in the 3-dimensional case, we assume isotropic strain hardening. We use updated Lagrange procedure, we update the geometry, and we use hexaedric elements of 8 knots. This is a 2-dimensional view, as many as 130,000 elements for the rod and 24,000 for the 3 balls. More than 150,000 elements. Very detailed mesh. With refined zones, and this is the refined zone in the 3-dimensional case. Let's go with the computer. It takes time, I think. Now, and this is the equation for hydrogen diffusion, the hydrogen diffusion model. Diffusion assisted by stress and strain, stress and strain assisted diffusion, in which the driving force, the hydrogen diffusion flux, J, contains 3 terms. The terms of concentration, delta gradient of concentration, typical fixed term, hydrogen diffuses as a function of the negative gradient of concentration towards the point where there is a scarcity of hydrogen, typical fixed term. In addition, the stress-assisted term, depending on the positive gradient of hydrostatic stress, hydrogen diffuses towards the points of maximum place, maximum hydrostatic strain, which is related one-to-one relation with hydrostatic stress. It's a mathematical question, could be hydrostatic strain in a place in the mesh. And finally, a more complicated term, the strain-dependent term, through the solubility, the positive gradient of solubility, which is itself a function of the cumulative plastic strain, which indicates mechanical damage and conditions diffusion, because plastic strain include dislocation, they are hydrogen traps, but they in addition transport hydrogen. Now we are improving our modeling, including trapping, apart from plastic strain. Trapping in the Magnat-Foster sense. We presented 2 years ago in Moscow the first equation in the Yuri Matvienko conference. Then the hydrogen diffusion model contains this equation for the equilibrium concentration. Hydrogen content in the burning for a long time, infinite time in theory, diffusion can be estimated by the steady state equilibrium concentration Cn, affected by the stress-strain state. This is a function of the gradient of hydrostatic stress, Maxwell-Boltzmann type, and the solubility is also included with the strain-dependent term solubility. And C0 is the concentration of equilibrium for the hydrogen, for the metal free of stress. Hydrogen in the metal free of stress. Let's go to the mechanical analysis. The distribution, we have analyzed in the 3 terms. This is quite multiaxial, the 3 terms of the stress tensor. This is the radial stress. This is the contact between the ball and the rod. And here we have the radial distribution. This is the contact with a concentration, and we have negative radial stresses. 0 degrees is just the plane of the contact, and different angles for the contact plane. With different angles, the concentration of stress is relaxed as the angle increases from the θ0, which is the contact plane. Then we have localized radial stress at the contacting zone, 0, 120 and 240, symmetry, 3 planes of symmetry, progressively vanishes with depth, of course, the depth from the contact here vanishes. This is the maximum concentration, negative stress, and with the θ coordinate as we depart from the contact plane, and maximum stress at contact surface. With regard to hoop stress, similar distribution. The hoop stress, again concentration and compressive in the contact area, relaxed in deeper points, and also relaxes when the angle increases from the contact plane. Localized at the contacting zone, 0, 120, 240, progressively vanishes with depth and θ coordinate, narrow affected zone. This is the zone of compressions, a strong compression due to the rolling contact fatigue, and maximum stress at contact surface. Negative stress. With regard to axial stress, similar distribution, again contracting zones have the maximum distribution, and it vanishes with the increase of the angle. In this case, not with the increase of the angle, with the increase again of the angle, and also with the distance to the contact point. Progressively vanishes with depth and θ coordinate, narrow affected zone, and maximum stress at contact surface. Let's go to the strain. The radial distribution with concentration in the contact area, but no different between the different angles. It seems that it is accumulated over a ring, and it does not strongly depend on the angle. Localized only over a plastic zone spreading of, roughly speaking, 300 micrometers. Outside of contact plane, no plasticity is generated. We are below the yield strength of the material. And with regard to the hoop distribution, we have this concentration in the contact plane, but we have minimum. And with a waving distribution, we have higher strains at different angles from the contact plane, because they are cumulative plastic strains. A slight local maximum close to θ0 contact section. This effect is progressively vanishes with depth, that's logical, and it slowly increases with θ, with maximum more or less at 45. You see this slight increase. We have a local minimum, a local maximum, and the trend is slightly increasing as we separate from the contact plane, as the angle increases. With regard to the axial distribution of equivalent plastic strain, of course, localized only over contact vicinity, and for axial distance higher than half millimeter, there is no plastic zone. As the height increases, the distribution vanishes, separates from the contact plane, from the contact area in axial distance. And with regard to radial distribution of hydrostatic stress, which is the 1/3 of the trace of the stress tensor, we have similar distribution. Compressive hydrostatic stress, that's the key relevant variable for hydrogen diffusion. It means that there is an inward positive gradient. Hydrogen is pumped from the surface to the inner points because of positive inward gradients, negative radial gradients, but positive we consider the X variable, the opposite from the surface to the inward point. The inward gradient is positive, but the boundary condition, the hydrostatic stress at the boundary is strongly negative. Then that's contradictory. On one hand, we have few amount of hydrogen supply because this negative hydrostatic stress at the boundary, but this small amount is strongly pumped because this very pronounced hydrostatic stress gradient, inward gradient, positive toward the inlet point, which is predominant, we are going to say, with the distribution of concentration. It progressively vanishes with depth, it approaches zero in the inner points. This is the concentration, negative at the boundary, positive inward gradients, hydrostatic stress with this is the driven, hydrostatic stress driven component of hydrogen. And regarding Hooke distribution of hydrostatic stress, again we have a minimum at the contact area, a strong minimum, and more or less uniform distribution for different angles. Local distribution in the vicinity of the contact plane, maximum is located at the contact plane exactly, at zero, at deeper points, 350 micrometers, homogeneous distribution. For different distances, we have a homogeneous distribution outside this area. With regard to the axial distribution, too many slides, the maximum at 0 degrees, and at deeper points, homogeneous distribution. Also, it vanishes with the depth. And let's go to the next slide. With regard to hydrogen diffusion, we have this radial distribution of hydrogen concentration for infinite time, equilibrium hydrogen concentration, normalized in dimensionless terms, divided by the equilibrium concentration for the metal free of stress, stress-free metal, equilibrium in the mesh, and we have again this, it tries to follow the hydrostatic stress profile. We have minimum at the boundary, few amount of hydrogen at the boundary, but strongly pumped, strongly driven because of the inward gradient, positive gradient of hydrostatic stress. For different angles, the maximum is for suppressing for 45 degrees, and for 0 degrees we have the lowest distribution, and for intermediate degrees, intermediate distributions. And now some comments. Theta 0, negative hydrostatic stress, gradient, negative radial gradient towards the right hand side, but the inward gradient with the X variable, the penetration depth, not the radial coordinate, they are opposite. The inward gradient is positive, then lower concentration because of this boundary condition. Predominates the negative hydrostatic stress at the boundary over the positive inward gradients. And as the distance to the contacting bar, to the contact plane increases, the concentration increases. Maybe because the predominance of this strongly negative hydrostatic residual stress at the boundary vanishes as we are far away from the contact plane. With regard to the Hooke distribution, we have this shape with the local minimum and more or less uniform, with a maximum more or less at 20 degrees of concentration. Now is hydrogen concentration normalized in dimensionless terms, equilibrium hydrogen concentration for infinite time, and divided by the concentration for the free stress metal. This is the Hopf distribution. Higher hydrogen amount out of the contact plane, theta 0. Here we have the minimum. Then hydrogen is expelled from this heavily compressed contact area, and maximum equilibrium out of the plastic zone, more or less at a depth of 260 micrometers at an angle of 20 degrees. I missed the pointer, but it's a good exercise. Axial distribution, here again we have for 0 degrees, and it vanishes as we are in heights different from the local area where we do have the contact. Higher amount out of the contact plane 0 degrees, and maximum out of the plastic zone. And finally, the conclusions. In a boron rod test, non-uniform plastic strains are generated in this contact plane where the pressure applied to the rod exceeds material yield strength, located at a maximum depth of 300 micrometers. Elevated compressive stress appears in the vicinity of the rod surface. It is progressively reduced at the distance from such a surface, increases in both radial and circumferential directions. Hydrogen is accumulated out of the contact plane, where an enormous reduction of hydrogen amount is achieved for a long time of exposure to the harsh hydrogenated environment. Due to the strong compressions, we see that these boundary conditions, heavy compressions, predominates over the inwards gradients. The key point here is the amount of hydrogen available for inwards diffusion, more than the velocity of inward diffusion. That's the real conclusion. And now the meta-conclusion, the epilogue, the conclusion over the conclusions. The maximum concentration of hydrogen appears in place with a circumferential coordinate, not 0. It escapes from the contact plane 0 degrees. Coordinate of 20 degrees, this is the maximum. Hydrogen escapes from the contact 0 degree plane to 20 degree planes from the contact plane at a depth, not just at the contact. Again, it escapes from the contact where there is few amount of hydrogen, and it concentrates for a long time at 250 micrometers from the surface of the cylinder. That's all. Thank you very much for your kind attention.